Hi, so this is video 2 in our second renal lesson, and what I'm going to do is I'm going to cover the concept of clearance in this video. Now, clearance is the result of what renal physiologists and what renal doctors consider to be a problem, and that is how to measure kidney function, okay? You can't just measure the plasma concentration of a substance ordinarily and say, okay, that's a measure of how well the kidneys are working. The substance went up, so the kidneys must not be excreting it enough, because the plasma concentration varies for a lot of factors. You can increase the production of that substance, and that'll make the concentration go up. There are all kinds of reasons why the plasma concentration might vary. Okay, so you can't really use that as a measure of kidney function for any particular substance. And similarly, you can't use like the urinary concentration, because that varies so much. If I drink a lot of water, my urine becomes dilute, and you can never really tell, how much of it is due to the dilution, how much of it is due to the fact that your kidneys are handling the substance poorly. So renal physiologists needed a way, and this translates to medicine as well, you need a way to measure the function of the kidney. And so the solution to this was the concept of clearance. Clearance is the measurement of the amount of substance that you're excreting, but instead of measuring like milligrams of that substance, what you do is you measure the volume of plasma that's cleared of this substance. Another way of saying that is, it's the amount of substance that you've excreted in units of volume of plasma, okay? So let me take a little bit more of a look at that here. So here is our substance, our blue dots, and it's being freely filtered. So this is our freely filtered blue dots, okay? And because it's freely filtered, 20% of this got filtered. It's the same concentration here at the top in the Bowman's capsule as it is in the glomerular capillary. So if we look at the plasma as it exits this glomerulus, if we look at the amount filtered, you can almost say that some of this plasma got filtered. The amount of substance filtered cleared this much of the plasma of that substance, okay? In other words, I have 6 dots here, so I cleared 6 dots worth of volume here of plasma of my blue dots, okay? So this is the amount of blue dots that are cleared. You filter this much plasma with your 6 blue dots, the volume of plasma is actually reabsorbed. I showed you that at the very beginning of the first video. Virtually everything filtered here, 99.2% or whatever is reabsorbed. So the volume ends up back in the plasma, but the blue dots don't. So we say that this volume of plasma was cleared of blue dots. It was 6 dots worth of plasma, okay? And we can use that as a measure of how the kidney is functioning, okay? So that is the concept of clearance. So how do you calculate clearance? Well, first you need to calculate the amount of your substance X that's excreted in units per time. So we have the urine concentration of the substance, let's say milligrams per mil. We know the volume per minute of urine that is urinated, produced. So that gives us the amount of X, okay? Then what you do is you divide by the plasma concentration of X, and that gives you the clearance in milligrams per minute, okay? So we have milligrams per minute of X in the numerator here, the urinary concentration times the volume per minute, and we divide that by milligrams per mil. That would be our plasma concentration, and that gives us milliliters of plasma per minute, okay, or the volume per unit of time that you have cleared of substance X. And that's how you calculate this. And this formula is convenient because the urinary concentration, the plasma concentration, and the volume of urine produced are fairly easily measured, Okay, so these are nice measurable variables that you can use to calculate the clearance. Okay, so let's try to apply this, and let's start with the clearance of a substance called inulin. Now, inulin is a polysaccharide. It's not naturally occurring. So as a physician, you would give this IV, and you would probably give a constant drip of it, a constant amount per minute. Okay. And this is a nice substance because it's freely filtered in the glomerulus and it's not reabsorbed or secreted. So that makes this fairly simple. All the inulin that's filtered ends up in the urine. You don't reabsorb any and you don't add any in the renal tubules by reabsorption or secretion. Okay? So what that means is that the clearance of inulin is the GFR. The amount cleared is the basically the amount of plasma filtered here, okay? Because we're not reabsorbing or secreting. I'll get to reabsorption and secretion and what they do here in a minute. So if the GFR is the clearance of inulin, then what you can do is you can continuously infuse inulin and measure the urinary concentration of inulin and the volume of urine produced, and you divide by the plasma concentration of inulin. That can give you a very good measure of what the glomerular filtration rate is, because all you're doing is filtering the inulin, so everything that ends up in the urine is the amount that was filtered, okay? And therefore, the amount of plasma that is cleared of inulin is equal to the GFR, okay? The amount of the plasma that was filtered, okay? So, again, you know, this isn't something you're going to do a lot as a physician because it's a pain in the rear to infuse this stuff. It's kind of a mess. But nevertheless, if you really need to know the GFR, this is the way it can be done, okay? So let's look at, we already said that if all we do is filter and we don't do anything else, the amount that we've cleared is equal to the amount of plasma that we filtered. Okay, because this is 6 dots worth, we actually cleared 6 dots worth of plasma, and that is the amount that we excreted if all we did was we filtered, okay? Now, if we reabsorb and we add triangles, we filter 6 triangles, now we reabsorb and add 3 triangles back to the plasma through reabsorption in the tubules, and we only excrete 3 triangles, that reduces our clearance. So now this pink box was 6 triangles worth. Now we've added 3 triangles back, so now my clearance is reduced to about half of what it was. So reabsorption reduces my clearance because it adds substance back to the plasma and it reduces the amount of plasma that's actually cleared of the substance. Okay? On the other hand, secretion of a substance will increase its clearance. So here I've filtered 6 plus signs worth of substance, okay? And that's 6 plus signs worth of plasma, okay? And then look, because I'm secreting, I'm also adding more plus signs from the plasma into the renal tubule. So that means in addition to what I cleared when I filtered, I'm also clearing more as I transport plus signs into the renal tubule. And so I've actually added to the clearance, and instead of 6 plus signs, I have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? So now I've cleared 9 plus signs worth of plasma instead of 6, because I secreted 3. I filtered 6 and secreted 3. And that means I cleared more of the plasma here of that substance. All right? So reabsorption reduces clearance, secretion increases clearance. So let's look at the extreme example of this. And that's clearance of a substance called para-aminohippurate, or henceforth known as PAH. Okay, this is also not naturally occurring, but it is convenient to give for a different reason. PAH is almost entirely secreted. So that means that not only are you filtering PAH, but you're secreting PAH. You're adding it from the plasma or the interstitium back into the renal tubule down here, and you're adding so much of it, and you're doing it so powerfully that you basically remove all the PAH from the plasma. 90% at least. So if we remove all the PAH, that means that the amount of plasma that I've cleared of PAH is basically equal to the renal plasma flow, because I've cleared everything. Everything that entered here ended up in the renal tubule. And so I cleared all this plasma of PAH. So this is a convenient, well, not very convenient way, but it is a way of estimating renal plasma flow. The renal plasma flow is the clearance of PAH. If I take urinary PAH, multiply it by the volume per minute, divide by plasma concentration of PAH, I get the clearance, and that is effectively all the plasma that entered the kidney, okay? So I've effectively cleared all the plasma of PAH. That means the clearance of PAH is equal to the renal plasma flow. And if I want to calculate renal blood flow, what I can do is, because I know that 43% of the blood is red blood cells, I can take the clearance of PAH, which is the plasma flow, and divide by 0.57, which is the volume of plasma per liter of blood, and I'll get renal blood flow, okay? All right. So again, here's what's happening with PAH. Let's say I have 70 milligrams per minute. That's entering the afferent arteriole. That enters the glomerulus. Let's say 10 milligrams per minute are filtered. Okay, and that means that 60 milligrams per minute are exiting through the efferent arteriole. 70 minus 10. Okay, 60 exit, and then PAH is so powerfully secreted that virtually all of it is removed from the plasma here and put into the renal tubule, so that I end up with 70 milligrams per minute in the urine, which is exactly what entered the kidney. So everything got excreted, and I cleared everything, all this plasma of PAH. So the PAH clearance is 700 milliliters per minute, okay? That you'll recall a normal value is 625. This is a little higher than that. Those values vary. So first of all, recognize that this is an ideal situation. We have 0 milligrams per minute actually exiting the kidney. That probably does not take place in real life. There's probably a little bit left here because you don't actually secrete it all. You probably secrete more like about 90%. But nevertheless, this gives a very good estimate of renal plasma flow. Now just for grins, let's see what happens if I double the concentration of PAH. Now I have 140 milligrams per minute entering the glomerulus. I'm filtering 20 instead of 10 because I doubled the concentration entering. Therefore, I'm doubling the amount that I'm filtering, okay? And I have 120 milligrams per minute exiting the efferent arteriole. And now that enters my peritubular capillaries. And I have secretion that takes place. And in this case, my secretion is 80 milligrams per minute, not the entire 120, and I end up with 40 milligrams per minute left over. So why would that be? It's because I hit what's known as the transport maximum. So this involves transport processes that transport PAH from the plasma or from the interstitium into the renal tubule, okay? You guys will recall that there's a maximal rate at which these transporters can operate. There's a maximal rate at which any enzyme can operate. It's the Vmax. Okay? In this case, we're calling it the transport maximum. And if you hit that maximum, you're basically transporting everything you can. And you can't transport any more. So in this case, 120 milligrams per minute overwhelmed the system. And all I was able to transport was 80 because I hit the maximum amount that I can transport. And I had a residual of 40. So this is the kind of thing that can happen in the kidney. It happens with glucose and diabetes, and that's why you end up with glucose in your urine. You hit the transport maximum in terms of transporting glucose back, or reabsorbing glucose in that case. In this case, you've hit it with secretion. So recognize that concept and the fact that you can maximally saturate these transporters so that you just can't transport anymore, and the system's overwhelmed. Okay? All right, and finally we get to creatine clearance. And this is one that you're going to deal with a lot more as a physician, at least conceptually. Creatine is produced, it's a natural substance for once. It's produced in the body, and it's produced by muscle, okay? And its rate of production is pretty constant, assuming that the muscle mass is constant, okay? It's freely filtered, it's not reabsorbed, it's secreted a little bit, but not too much. So you can use it, it's close enough for government work. You can use it to estimate the glomerular filtration rate because it's not reabsorbed and it's only secreted a little bit, all right? If we look at the creatinine clearance, we have the urinary clearance times the volume of urine produced, milliliters per minute, divided by the plasma creatinine, and that gives us the clearance, and that's a pretty good estimate of GFR, okay? And that's something you can do just through measurements of creatinine in the urine and urinary production rate, and with the plasma creatinine, which you'll pretty much always measure. This is one way to get a really good estimate of GFR. Now, what you'll probably do more commonly is just look at the plasma concentration of creatinine. And this, because of its special characteristics, there's actually a well-established relationship between plasma creatinine and normal and glomerular filtration rate. So at a normal GFR of about 125, you'll end up with a plasma concentration of creatinine of about 1 milligram per deciliter. And this is a value that you'll look at a lot. If that value goes up, it probably means the GFR went down, okay? And this is the relationship between the two. So let's look at how that works. Here's my normal creatinine, and it's normally 1. Now let's say my GFR drops by 50%, okay? So if we look at what's happening normally, we have the amount of creatinine being produced, and it's exactly balanced by the amount of creatinine being excreted, okay? And at a normal GFR of 125 and a normal creatinine concentration of 0.01 milligrams per mil, that's 1 milligram per deciliter, we end up with 1.25 milligrams per minute being excreted. And normally that is exactly how much is being produced. So you're at a steady state, you're producing 1.25, you're excreting 1.25, and everything stays constant in the body. You're homeostatic, okay? So now let's say that we reduce the GFR by 50%. So if my GFR goes down 50%, now I've got my 0.01 milligrams per minute, but now it's multiplied by 62.5 instead of 125. I'm at 0.625 milligrams per minute. So now my production is still 125, but now I'm only excreting half of that. So what happens as a result is the plasma concentration of creatinine rises. And it rises until the amount of creatinine excreted is equal to the amount produced. Well, the amount produced is 1.25 milligrams per minute. And now, if my plasma concentration rises to 2 milligrams per deciliter, and I multiply that by my new GFR, I'm back to 1.25 milligrams per minute. So when my plasma concentration rises to 2 milligrams per deciliter, now I'm excreting the same amount of creatinine that I'm producing with half the GFR. So you can see that my plasma concentration of creatinine has risen as my GFR is dropped by 1/2, my creatinine is doubled. What happens if it drops to 1/2 of 62.5, 31.25? My plasma concentration of creatinine doubles again, and it becomes 4. 4 milligrams per mil times my new GFR of 31.25 gives me 1.25. That's the point at which I'm excreting exactly as much as I'm producing. Okay? So this is the reason why this relationship looks the way that it looks. A lot of people always ask us, why isn't it linear? It's not linear because this relationship actually cuts in half every time, this doubles every time this cuts in half, and that's not a constant slope. You can see the relationship and how it's formed. And it's this way because the plasma concentration is always going to rise until it hits the point where the excretion is equal to the production. And if the GFR drops, then the plasma concentration is going to have to go up until that happens again. Okay? All right. That's all I've got. Thank you for your attention. I'll see you guys in the classrooms.